In this video, we'll cover 7 Chapter 10 exercises. What is the intermediate involved in the following reaction? So, first step of this reaction, addition of hydrogen bromide to an alkyne, involves addition of proton to less substituted carbon, following Markovnikov rule. That will, of course, result in formation of carbocation on the other carbon of the triple bond. And that's actually A. B is not correct intermediate. That would be an intermediate in bromination, reaction with Br2. C is not correct. That would be anti-Markovnikov addition. It gets less stable carbocation. That would be less stable. And D is just not reasonable intermediate. Which of the following reagents reacts only with terminal alkynes and does not react with internal alkynes? To answer this question, you need to consider each of these 4 reagents. This is what we call closed question, which means that you have to consider 4 possible answers. And the best way to answer questions of this type is to eliminate 3 wrong answers and end up with one that is left correct answer. So we need to consider each of the 4 reagents and see which one would make difference between terminal and internal alkynes. And you may recall the difference between terminal and internal alkynes is that terminal alkynes have acidic hydrogen. Hydrogen proton that is bonded to sp hybridized carbon. Internal alkynes do not have them. So for that reason, terminal alkynes will react with strong bases while internal alkynes will not. That's an important piece of information and may be important in answering this question. So if we consider 4 possible answers, answer A, hydrogen with palladium in the presence of pyridine, that's catalytic hydrogenation with Lindlar catalyst, and both internal and terminal alkynes could undergo catalytic hydrogenation. So A is obviously not correct answer. B is oxymercuration-demercuration reaction, and again both terminal and internal alkynes react under oxymercuration-demercuration conditions. C, sodium in liquid ammonia, that's dissolving metal reduction, and again both internal and terminal alkynes undergo dissolving metal reductions. In each of these 3 cases, we had a case where it was carbon-carbon triple bond that underwent reaction, and so both internal and terminal alkynes underwent reaction with those reagents. It's D, the last one, sodium amide. That's strong base. Sodium amide has no effect on carbon-carbon triple bond, but as a strong base, it can deprotonate a terminal alkyne. So that's correct answer. Next question, reaction of 1-hexyne with dicyamyl borane followed by an oxidation gives, and now we have 4 possible choices, primary, secondary, alcohol, aldehyde, ketone. This is actually an open question, unlike previously it was closed. An open question is a question that you can answer without looking at 4 possible choices. Really the question is which class of compounds is obtained in a reaction of 1-hexyne with dicyamyl borane, or product belongs to which class of compounds. So to answer an open question, the best way is to answer it without looking at the 4 possible choices. Simply take pen and paper and write down the equation. So 1-hexyne reacts with dicyamyl borane, for example in THF as a solvent, to give corresponding vinylic borane or vinyl borane. And then upon oxidation, product is initially vinylic alcohol, which rearranges spontaneously to an aldehyde. And so on our own, without looking at 4 possible choices, we have figured out that product is an aldehyde. And now we match it with 4 possible choices, and we can tell that answer is C. Which of the following compounds is a suitable starting material for the reaction shown below? We have reaction of unknown compound with 2 equivalents of hydrogen bromide. Note that 2 equivalents of hydrogen bromide are involved, so stoichiometry is important, and product is 2,2-dibromopentane. We have to consider each of the 4 possible choices and find out which one is suitable as a starting material for this reaction. Choice A is 2-bromo-1-pentene. That compound with hydrogen bromide would indeed give 2,2-dibromo-pentane. It's a Markovnikov addition of hydrogen bromide, and that should be the product. But the problem is that reaction requires addition of only one equivalent of hydrogen bromide. One bromine is already present in the molecule, and it takes addition of only one equivalent of hydrogen bromide to give the reaction product shown here. This reaction involves two equivalents, so this cannot possibly be correct answer. B, we have 1-pentyne, and that actually is correct answer. 1-pentyne upon addition of two equivalents of hydrogen bromide following Markovnikov addition or addition through a more stable carbocation as the intermediate gives indeed 2,2-dibromo-pentane, and that's correct answer. We can consider remaining two answers, so C actually appears to be correct answer because in this case we have two carbons of the triple bond, an eternal alkyne, two carbons that have equal degree of substitution. Neither of them has any hydrogen, and each of them upon addition of hydrogen bromide would give the same carbocation. First initially vanillic carbocation, and then secondary carbocation with bromine substituent on it. But problem is that we would not expect any regioselectivity, or at least not much regioselectivity in this reaction. And so the product, or the products in this case, would be a mixture of 2,2-dibromo and 3,3-dibromo pentanes. And that's obviously not very good. That's not desired. If we want to prepare a certain compound, we don't want a mixture where one of the components of the mixture will be desired product. We want to get that compound as the sole product. So B is obviously much better answer. And finally, D is obviously not correct because compound is already dibromo compound, and addition of another molecule of hydrogen bromide to an alkene would simply add another bromine to the molecule. So in summary, correct answer to this question is B. Next question, what is the structure of the reaction product? And now we have an internal alkyne. Reaction of that internal alkyne is with sodium in liquid ammonia. That's dissolving metal reduction. And dissolving metal reduction results in reduction of an alkyne to transalkene, corresponding transalkene. So triple bond is reduced to a trans double bond. When we consider four possible choices, that's compound A. Sorry, I did not show B as correct answer previously, so it just popped up. But in this case, for this question, correct answer is A. B would have been correct answer if catalyst was Lindlar catalyst, so hydrogen in the presence of palladium and some catalytic poison such as pyridine. C and D are not reasonable answers. Provide the product of the following sequence of reactions. This is reaction of 2-pentyne, and it's a sequence of only two reactions. In the first step, 2-pentyne reacts with hydrogen in the presence of palladium and pyridine, and then the product of that reaction reacts with bromine. The best way to answer this question is to use pen and paper, write down the reaction sequence, product of each step, and that way answer it. So we start with 2-pentyne, and reaction with hydrogen in the presence of palladium and pyridine is a catalytic hydrogenation of an alkyne. Palladium with pyridine is Lindlar catalyst. Lindlar catalyst is what we call poisoned palladium catalyst, that means less effective palladium catalyst, and it is capable only of hydrogenating triple carbon-carbon bonds, but not double bonds. That means that it will hydrogenate an alkyne to alkene and leave alkene intact. And as you may recall, catalytic hydrogenation occurs in syn fashion. That means two hydrogens are added from the same side. In this case, actually for the overall outcome of the reaction, that may not be important because you're not being asked about stereochemistry. Nonetheless, product is cis as a result of syn addition. So it's cis 2-pentene. And then in the second step, addition of bromine across a double bond gives the final product 2,3-dibromopentane. In this case, we have syn addition of hydrogen and then anti-addition of bromine, and so that's not the question, but you could actually figure out stereochemistry, final stereochemistry of 2,3-dibromopentane. There are 4 possible stereoisomers, and actually only one of the 4 possible stereoisomers is obtained. What was the starting material for the following reaction? So in this case, we don't know the starting material. We have the reagent, ozone, and we have product, dicarboxylic acid. So first we have to look at reaction conditions. Reaction is ozonization, ozone in dichloromethane, typical ozonization conditions, and then workup is water, just water. That gives us a big hint, big piece of information. Because when water on its own is used in a workup, that means that starting material was an alkyne. So this is ozonization of an alkyne as starting material. If an alkene per starting material, then workup would require either reducing or oxidizing agent. And the fact that we have dicarboxylic acid as a product is an indication that starting material was cyclic and multiple bond, in this case triple bond, was oxidized and broken to give open chain compound. So 2 carbons of the carboxylic groups were in the starting compound bonded to each other, and in this case they were bonded to each other by a triple bond. So if we count the number of carbons, total number of carbons in this dicarboxylic acid, there are a total of 9 carbons. And that means that starting material was 9-membered ring with triple bond, or no 9. So that's a relatively simple question. If you know what the reagent does and how to work problem backwards, then that's a relatively simple question. And this completes Chapter 10 exercises.